So here we want to show you how you can use different types of tests to confirm the convergence or divergence for a series. So here we have the series 3n plus 7 divided by 4n squared minus 5. Now the first thing I want to do is I want to use the nth term test for divergence, because usually when we see a number written in this manner, that's usually the first thing that we try to do. So with the nth term test, we will set this up. The limit as n approaches infinity from 3n plus 7 for 4n squared minus 5. Now, remember, we have to go back to our old rules where we divide through by n squared. And since n, the degree of n is higher in the denominator than in the numerator, this would be equal to 0. This limit will go to 0. But by the nth term test, this would be inconclusive. This would be inconclusive. So next, we want to use the ratio test. Let's use the ratio test here. I'm going to erase this one, and let me write this out here. So the ratio test, once again, we let limit as n approaches infinity, and we replace n with that n plus 1. And remember, we divided by the original. Okay, and now in the numerator we would have 3, after we distribute this, we would have 3n plus 10. Over, this would be 4n, what would that be, n squared? Let's do it on the scratch paper. Okay, this would be 4n squared, and this is all this. You all could check the mathematics here. Remember, whenever we divide by a fraction, we multiply by the reciprocal. Now, after we simplify this, everything, and I'm going to put it under here, this would be 12n cubed. Everything else would follow. Of course, you could simplify it out. Everything under here, after we multiply it out, the leading term would still be 12n cubed. Now, just due to the space that I have, we're not going to go into that. But once again, 12n cubed over 12n cubed, we look at the highest degree. That would be 12 over 12, which is equal to 1. So once again, by the ratio test, it's inconclusive. So next, we want to look at the limit comparison test. We're almost out of tests that we can use. So let's look at the limit comparison test. All right. So now with the limit comparison test, we have 3n plus 7. And remember, we just have to look at the first one. And we're going to compare this to n over n squared. We're taking the highest degree of n, which breaks down to 1 over n. Now, what does this look like? Remember, we break this down, and I just did it piece by piece. We break this down until we could get p is equal to 1. So this series diverges. This is a P series. Okay, it diverges. So the only thing that we have to do now, remember, is confirm it. So we're going to go back to it. Okay, that's 3n plus 7 over 4n squared minus 5 over 1 over n. Once again, just remember, when we divide by a fraction, we're going to multiply by the reciprocal. Even though that's a very old rule that you probably learned in elementary school, we do not want to get away from it. So this is going to be what? 3n squared, okay, plus 7n. And this is going to be what? 4n squared minus 5. All right, so when we look at this one, remember all of the rules, they have the same degree of n in the numerator, so we're going to look at the leading coefficients. Okay, so this is 3/4. So now, we have a finite positive number. So that confirms it. Okay, so this series diverges if you go back and look at the rules for the limit comparison test. So this is just an example of how you use the different tests. Now, preferably, you will use the limit comparison test for the first test. But just in case, this is how you can go through each test to confirm it. So we had to go through 3, but the whole idea for these tests is to start learning how to identify the test and kind of knowing what to use when. I always talk about this in class, but knowing when to use the screwdriver and when can you just use the butter knife. All right, so we have to definitely know how to win. And the more practice you get, the more series that you work, the easier it is to tell, which test to apply to each series.